Hey, welcome back everyone. Hope you all had a good weekend. So today we're going to be starting a review on probability. Before that, actually, in-class review on the previous material. So please take a couple of minutes to try to work this out. Okay, let's go over this question. So which of the following about ridge regression is true? So we're actually going to start with, probably makes more sense to start with C here. So compared to ordinary least squares, ridge regression adds a regularizer. So that one is definitely true. So the regularizer is plus lambda 2 norm squared of W. Okay, so because it adds a regularizer, there's a kind of a weight, there's kind of a lambda constant that we can choose. So that's actually an additional hyperparameter in ridge regression. So that's why D is also true. So however, even though there are more hyperparameters, the number of parameters is still the same as the ordinary least squares because the parameters are W, so E is false. Okay, and because we're adding this regularizer, the loss function becomes a strictly convex function. So F is true. And because the loss function is strictly convex, there's always a unique optimal parameter vector. So B is true. Remember, if you recall, x transpose x plus lambda I is always invertible. So we can always determine a single W. And the whole point of ridge regression is to penalize large values of W, which can be a sign of overfitting. So yes, ridge regression is less prone to overfitting compared to ordinary least squares. Okay, so hopefully you got most of that. And now we're going to continue on to probability review. So we're going to start with the very basics, but then going to go over things pretty quickly. So first, some terminology. So a sample space, usually denoted omega, is a set of all possible random phenomenon. So for example, if you toss two coins, the sample space would be head, head, tail, tail, head, tail, tail. So that's the set of possible outcomes. And event E is a subset of omega, so a subset of the possible outcomes. So for example, there used to be 4 elements in the sample space. Head, head, tail, head would be basically a subset of the sample space, right? So that would be an event. The entire sample space is also a subset of itself, so that's also an event. And also the empty set is also a subset of the sample space, so the empty set is also an event. Okay, and then the probability measure, sometimes just probability. It's a function that assigns a number to every possible outcome. So in the case of the 2 coins, each of these outcomes would be assigned a value of 1/4, 1/4. Or you can assign a probability or a number to any event, so any subset of this. So for example, the subset, which is second coin, turns out to be heads. So that subset, it would be this element head head, and also this element head head. So that subset gets assigned 1/2. Okay, and finally, random variables. So these variables, these are variables whose values depend on the outcome of a random phenomenon. So you may be the most familiar with these. So if we define a random variable xi to be equal to 1, if the ith coin toss turns out to be heads and 0 otherwise, so this would be a random variable. Its outcome depends on what happens when you toss several coins. We can also define a variable y to be equal to the sum of the xi's. So we can define more variables on top of other random variables as well. Okay, so let's keep going. So we're mostly going to be talking about random variables, and there are 2 types: discrete random variables, so random variables that take on values from a discrete set. So for example, a coin toss would be a discrete random variable because we can only get head and tail. Rolling a die, that's also the outcome of rolling a die, that's also a discrete random variable. We can also have continuous random variables, which take on a continuous range. So for example, you may know the uniform random variable defined on a continuous interval. You may also know the Gaussian random variable. So random variables need to be characterized by the probability distribution. So that basically tells us the probability that the random variable takes on different values or different ranges of values. So for both discrete and continuous variables, we can represent the probability distribution as a cumulative distribution function, CDF. For only discrete variables, we can use the probability mass function, PMF. And for continuous variables, we use the probability density function. And lastly, on this slide, the support of a distribution is the set of realization of the random variable where the probability is non-zero. So for discrete random variables, that would be where the PMF is non-zero. And in the case of continuous random variables, the support is where the PDF is non-zero. So hopefully you have seen most of these terms. If not, please go back and review. And now a summary of discrete versus continuous random variables. So for the discrete variables, we can use a cumulative distribution function that's defined to be this capital F subscript capital X. So capital F stands for CDF, and the capital X denotes which variable are we indicating, which variable is the CDF for. So this would be the variable capital X, and then we have the argument X, which represents the probability that the random variable capital X is less than or equal to this argument here. On the continuous random variable side, the definition is exactly the same. Okay, but for the discrete side, we need to define a probability mass function. So here we use little p to denote probability mass function. and then the capital X to denote this is for the variable capital X, and then the argument, which tells us this is the probability that the random variable equals the little x, the argument. For continuous random variables, it wouldn't make sense to talk about the probability that the variable takes on exactly some value. So instead of the probability mass function, we define the probability density function. So here we have little f, which stands for PDF, and then the subscript capital X, and the argument little x. So this doesn't mean the probability that capital X takes on the value of little x. This actually just means the derivative of the cumulative distribution function. Some common discrete random variables are Bernoulli random variables and categorical random variables. And some common continuous random variables are uniform random variables and normal random variables, or sometimes called Gaussian random variables. Okay, again, hopefully this should be review. So that's why we're going through it pretty quickly. I guess turning the previous slide into some graphs. For discrete random variables, here we're seeing a uniform random variable, which can take on values between a and b at some particular discrete values. And the probability that the random variable takes on each of these values is equal to 1 over n, where n is the number of different discrete values. So this would be the PMF, probability mass function, this one. And on the bottom, we have the CDF, the cumulative distribution function, which tells us the probability that the variable takes on a value less than or equal to whatever argument we plug in. So for example, the value here tells us that the probability that the random variable takes on a value less than this particular value would be equal to I over n, because we're adding everything before. On the continuous random variable, we have a Gaussian random variable as an example. So this is the probability density function, the familiar bell curve. So that's this one. Okay, if we integrate from negative infinity to a particular number a, that value, the area under the curve, is the value of the CDF, cumulative distribution function. So this is the probability that the random variable takes on a value less than or equal to a. So because the area underneath here is the value down here, that means that the derivative of this function must be the value of the PDF. So that's what we had here. Okay, let's continue. Okay, so some basic properties of random variables. So for discrete random variables, the probability mass function is always going to be greater than or equal to 0 for any input, because the probability of any outcome is always non-negative. And of course, all of them must also be less than or equal to 1, right? Probabilities cannot be greater than or equal to 1. But the summation over all possible outcomes of the probability mass function is equal to 1. And the cumulative distribution function, capital F, is just probability that capital X less than or equal to less than or equal to little x. So that's just summing everything, summing the probability mass function for all the values of x less than this particular value indicated by little x. So then we use a different index x tilde to represent this, to represent what we're summing over. On the continuous random variable, it's actually pretty similar. We have the cumulative distribution function. This is actually the probability distribution function, which is the derivative of the cumulative distribution function, capital F. So the capital F is always non-decreasing, because the larger a value of x you plug in, the probability that the random variable takes on something less is always more and more likely as little x increases. This also means that f the probability density function is always non-negative as well. So probability density function is always non-negative, and then the CDF is always non-decreasing. For the continuous case, the probability that the random variable takes on an exact value, little x, is always equal to 0 for every x. So it's important to remember that the PDF is not the same as the probability that x, the random variable capital X, takes on the value of little x. So that's kind of different from the discrete case. Another difference is that the PDF may be larger than 1. It could actually be arbitrarily large, but the integral, so the entire area under the PDF must be equal to 1. So potentially you could have a PDF which has a very high peak, but then very narrow, so that the area underneath the curve is still 1. So that means because the PDF could be arbitrarily large, the CDF could then have arbitrarily high slope because it's the integral. And finally, the CDF, capital F x of x equals to probability that capital X less than or equal to little x. So this is just integrating from negative infinity up to x. And then of course we have to use a different variable to denote the variable that we're integrating. Okay, so let's talk about some common probability distributions. Probably the most common one is the Bernoulli distribution. As a shorthand, if we have a variable x which is distributed with the Bernoulli distribution, then we write x is x tilde Bernoulli of p. P is a parameter of the distribution. So what that means is the probability mass function is equal to p if x equals to 1 and 1 minus p if x equals to 0. Only two outcomes. The outcome where x equals to 1 has probability p. So this is actually very easy to understand, hopefully, but mathematically it can be a little hard to work with, especially in machine learning when we need to take derivatives a lot. So a more mathematically convenient form is to write these two cases in one line. So you can write that as p of x times 1 minus p to the power of 1 minus x. So this looks a little impossible if you have never seen it before, but the key is that x can only take on two different values. So x is not continuous. So all we have to do is to check what happens when x is equal to 1 and what happens when x is equal to 0. So in the case when x is equal to 1, we have 1 minus x becoming 0. Because of that, this whole term becomes 1 because it's something to the power of 0. And of course, when x is 1, p to the power of 1 is still p. So then we can ignore the x, right? So that's what happens when x equals to 1. It agrees with the definition of Bernoulli variable. On the other hand, when x equals to 0, we can see that now the first term is now to the power of 0, so that whole term becomes 1. The second term here is we have 1 minus x, 1 minus 0, so we can safely ignore the minus x. Now we have something to the power of 1, so we can safely ignore the 1 as well. So for x equals 0, we also have the probability mass function is equal to 1 minus p, right? So it agrees with the definition. So this is actually very convenient, writing everything on one line, even though the function has two cases. Okay, generalization of the Bernoulli variable is the categorical distribution. So this is basically saying that the probability that the random variable big X equals to little x is just equal, where little x can be a value from 1 to k, while the probability is P1 to Pk. So this is pretty common in machine learning, especially if you're doing something like object recognition, for example. So these could be the possible outcomes of X could be could represent the different objects, and then the probability could be the probability that a model predicts for that particular object. Again, this is a bit hard to work with because it has so many cases, but we can convert everything into one form, one line, by using this convenient form. So basically we have the product from I equal to 1. So this big pi thing is the product. It's the same thing as the sigma notation for sum, but then this is product. So product from I equal 1 to n of pi to the power of the indicator of x equals to I. So this is the indicator function. Basically, this thing inside a bracket equals to 1 if x equals to I, and 0 otherwise. So let's take a look at why this is a short form. So suppose x equals to, let's say, 2. If x equals to 2, this term will be 0 unless I equals to 2. And this will be 1 if I equals to 2. Right? So that means this whole thing will be 1 whenever I is not equal to 2. So then they don't even show up in the product because that term is 1. The only term that is not 1 in the product is going to be when I equals to 2. In that case, you can safely ignore the exponent and you simply have P2. Right? So in the end, we just get P2. So basically, this agrees with the definition of the categorical distribution. So now let's take a look at some common continuous distributions. The first one is a uniform distribution, or x tilde uniform AB. The A and B specify the interval of the distribution. So now we have to take a look at the PDF. Fx of x equals to 1 minus b over a if x is within the range a to b, inclusive, and 0 otherwise. The support of x is from a to b, inclusive, and the CDF is just going to be 0 before we get to a, 1 after we get to b, and then a linear line connecting a and b, 0 to 1. Okay, another one is the normal distribution. So here we actually write x tilde script n of mu comma sigma squared. So a lot of times we actually call this the Gaussian distribution. So the PDF looks a little bit complicated. We have some 1 over square root 2 pi sigma squared, and then exponential negative x minus mu squared over 2 sigma squared. Okay, so maybe we need to get familiar with all of these Greek letters if you're not already. Mu is the mean of the distribution. It's basically the center of this peak. So the distribution actually looks like a bell curve. And then the sigma is basically how wide this peak is. So for example, the dark blue one. For the dark blue one, we have mu equals 0. So the peak is at the center, and sigma squared equals 0.2. If we keep the mean at 0, but then sigma squared becomes 5, then we get the orange curve, which is very wide, but it's still centered at 0. You'll notice that it's also a bit shorter because we need to keep the area under the curve equal to 1. The green curve basically just has mu equals -2, so that's why it's shifted a bit to the left. The support of a Gaussian distribution is all the real numbers. So every real number has a PDF greater than or equal to strictly greater than 0. A special normal distribution is the standard normal distribution, which has a mean of 0 and a variance, sigma squared is called the variance, of 1. It's a property of Gaussian distributions that if you add a constant to a variable, if you add a constant to a standard normal distribution, you will shift the mean by that constant. And if you multiply the standard normal distribution by some constant sigma, then the variance will then the variable becomes a normal distribution with variance sigma squared. So combining these two, we can always construct any Gaussian random variable using the standard normal distribution. So mu plus sigma z would be distributed as normal of mu and sigma squared. Conversely, you can take any normally distributed variable, x, if you subtract the mean and then divide by the square root of the variance, also called the standard deviation, you will get back a standard normal distribution. Okay, so a lot of things at once, but hopefully you've already seen all of this. So just a bit of refresher. Okay, so far we have been focusing on one random variable. But what if we have multiple random variables, which is obviously very common, and sometimes the different random variables may be related to each other. So for example, if we define a random variable representing tomorrow's temperature and another random variable denoting the amount of snowfall, then these two random variables would be related to each other. They will affect each other. Okay, so now we're actually going to change the notation a little bit to make things a bit simpler. We'll be consistently using capital letters to denote random variables. And then the corresponding lowercase letter will denote a realization of the random variable. So because we're always using the same capital and lowercase letters, we can drop these subscripts, which are kind of they don't look that neat, basically. We also want to make things a bit more consistent between continuous and discrete variables. So we're simply going to use P of x to represent the PMF if the variable is discrete, and then also represent the PDF if the distribution is continuous. So P of x could be a probability mass function or a probability distribution function, or probability density function. For the CDF, we're simply going to be using the capital letter F. Okay, and then PDF, PMF, lowercase p. So that will simplify the notation a little bit. Okay, so let's take a look at two different random variables, and then we're going to take a look at in general. So for two different random variables, the CDF is defined to be the probability that x less than or equal to little x, and y less than or equal to little y. In the discrete case, the PDF of xy means probability that x equals to little x and y equals to little y. So the key here is and in both cases. For the continuous case, it's a little bit more mathematical. It's just going to be the partial derivatives, the second partial derivative with respect to x and y of the CDF. On the right figure, we have a running example. So suppose we define two different random variables. X represents the car type, and y represents the manufacturer. So in the discrete case, so this is obviously a discrete case, right? Because x and y only take on a discrete set of values. So all of these bars represent the values of the PMF. In particular, this bar represents the probability that the model, the car type, is minivan, and the manufacturer is European. Of course, all of these bars add up to 1. To generalize to any number of variables, we simply keep on adding n's, and then xi less than or equal to little xi. So it should be pretty straightforward. For the PMF, it's the same thing. So that the PMF represents the collection of xi's equal to little xi's. So kind of the combination is basically talking about a combination of the values of each of the random variables. For the continuous case, be no such simple explanation for the PDF, but it's basically going to be the same kind of partial derivative as above, but doing it n times with respect to all of the variables. Okay, so next, marginal probability distributions. So previously we looked at P of xy. So if you start from P of xy and you would like to get P of x, then you can sum over all the possibilities of y. And in the continuous case, you would integrate over all the possibilities of y. Pictorially, the marginal probability distribution simply represents kind of the heights of each of the rows or columns. In this case, I guess we can call that a column. So the marginal probability distribution is just going to be, in this case, the probability that x equals a minivan. So that's going to be equal to the sum of all of these. So we're summing across the other direction. So you can also ask, what is the probability P of x equals to the sedan? For that one, you would sum up across y, right? So if you sum across y for all possible x, you will basically just get P of x. So hopefully that makes sense. So P of xy in this case has 12 different possibilities, 12 different possible numbers to represent P of x comma y, and then we can use 4 numbers to represent P of x. And the way we get those 4 numbers is to do the summation across the you would sum over y. So you sum these 3 bars to get P of x equals sedan, sum these 3 bars to get P of x equals to minivan, and so on. So you get 4 numbers. Okay, in general, we can kind of generalize it to more than 2 variables. It's just going to be the same. So suppose that you have n variables in total, and you would like to only look at the probability density function of the first of m of the variables. What you do is you basically sum over the other variables. So the summation looks a bit complex, but basically we're just summing over all the possibilities for xn plus 1 all the way up to xn, leaving the first n variables alone. So that's the discrete case. For the continuous case, we're just going to be integrating over all the possibilities of the variables that we don't want remain in the end. This procedure of summing or integrating out the other variables that we don't want to keep, that's called marginalizing out xn plus 1 all the way up to xn. So that brings us to conditional probability distributions. We write that as P of y given x, which is defined to be P of x comma y over P of x. So that's the joint distribution and that's the marginal distribution. We can expand the bottom according to the previous slide. So P of x could be one of these cases depending on whether the variables are discrete or continuous. So we can write them here. And the interpretation is basically, so P of y given x is the probability that we have a value y, let's say European, given that our car is a minivan. So what is the probability that the manufacturer is European given that our car is a minivan? Because we're given that the car is a minivan, we only have to look at these three bars. We add them up and then we divide this red bar by the sum of the three bars. That gives us the conditional probability. It kind of makes sense, right? Because we know that the car is minivan, so we only have to consider these three bars. Out of all the outcomes for a minivan, what is the probability that the manufacturer is European, right? So that's just that it's just taking the red bar divided by the sum of the three minivan bars. Okay, so you can kind of see this calculation up here. In general, we could have a conditional distribution over, let's say, the last few variables from n plus 1 to n, given the first bunch of variables. In this case, we just take the joint distribution and then divide by the part that is given. Okay, and then we can write down, for the denominator, we can write down the marginal distribution according to the previous slide. Okay, for the continuous case, the denominator would be a big integral. Next, the chain rule of probability, which is very, very useful. It actually comes from the conditional probability distribution. So this is what we defined. P of y given x equals to P of xy over P of x. If you rearrange this equation by multiplying P of x on both sides, you would just get P of xy equals to P of x times P of y given x. The way I like to remember this is that you can turn something like x and y into y given x by multiplying by P of x to compensate. You can turn the comma into a given, and then if you do that, you need to multiply by the thing that is given, so P of x. In general, if you have many variables, you can keep doing this. So you can actually write P of x1, which is kind of like this, the first term here, times P of x2 given x1, like the second term. But then with many variables, you keep going. You do P of x3 given everything before. And then P of x4 given x1, x2, x3, everything before. And then eventually P of xn given everything before. So that kind of, hopefully that makes sense. But the way you can remember this is that obviously this is P of x1. This thing will be P of x1, x2. So that means if I have P of x1, x2, and then I multiply by P of x3 given x1, x2, this whole thing becomes P of x1, x2, x3. And then the next thing becomes P of x1 to x4, right? And so on. And then eventually we actually get P of x1 all the way up to P of xn. So that's why the chain rule works. So many of you probably know this this rule, but maybe you don't know that it's called the chain rule of probability. So now we're gonna repeat a lot of the same thing, but for the conditional case. So the first one is called the chain rule of probability conditional case. Basically, what we're gonna see is that it looks exactly like the chain rule, except that everything here, on the given, every term here will be given an additional variable. And we're gonna call that z. So everything, so p of y given x, and then adding on z. On top, it used to be p of xy, but now given z, and then on the bottom, used to be p of x, now given z. So in general, in probability, we can always given some variable in every term, and that shouldn't change anything. All the laws, all the rules, they all work. In the general case, we have the chain rule for x. So we have p of x1, p of x2 given x1, and then p of x3 given x1, x2, and then eventually p of xn given x1 to xn minus 1. And then every term here will be given the same set of z variables, z1 to zl. Right? So everything is kind of abstract right now. So these are just potential variables that we could be given. But then if they're given everywhere, then we preserve the previous rule. Okay, again, let's continue forward with a very quick review of probability. So next we have independence. Two random variables are independent if, when you're given one of the variables, it doesn't change the PDF of the other. So p of y given x is exactly the same thing as p of y, no matter what x you're given. So knowing something about x doesn't tell me anything about y. And equivalently, knowing something about y doesn't tell us anything about x. P of x given y is equal to p of x for all y. From the chain rule, we know that normally p of xy equals to p of x times p of y given x. But because now p of y given x is just p of y, we can actually just multiply the marginal distributions to get the joint distribution. P of xy equals to p of x, p of y. So this will be an equivalent definition. If you have n variables which are all independent from each other, so mutually independent, then the joint distribution p of x1 all the way up to xn is equal to p of x1 times p of x2 all the way up to p of xn. We have to be a bit careful here, so mutually independent is important. Sometimes you could have a set of variables where if you're given, so every pair of variable could be independent, but three variables together may not be independent. So that would not be mutually independent. So one example is could be birthdays. So let's say that we have n people in the class, and x1 and xi represents the day on which we're born, the day of the year that the ith person is born, right? So we have n different birthdays. So I think we can pretty safely assume that between every pair of people, their birthdays would be independent. But then if you group three people together, the three variables are no longer independent, because if I know that two people have the same birthday, so if I know that I have the same birthday as person number 2, and person number 2 has the same birthday as person number 3, then I also automatically know that I have the same birthday as person number 3, right? So kind of knowing some relationship between 1 and 2, and then 2 and 3 tells us something extra about 1 and 3. So that's one case where we have pairwise independence. So every pair of variable is independent, but then once you get to a group of 3, suddenly they're not independent anymore. Okay, so mutually independent just means that no matter what information you're given about any other variable, your probability doesn't change for any of the variables as well. So now the conditional case, right? Again, whenever we talk about conditional cases, everything will be exactly the same, except that we're going to be conditioning on some additional variables for every term of all of these equations. So P of x given P of y given x and z is equal to P of y given z for all x. Okay, or we can swap x and y just like before. So, but now every term is given z. Okay, and then for the other equivalent definition, we have P of xy given z would be equal to P of x given z, P of y given z. Okay, again, same as before, but everything is given z. And down here, again, same as before, but everything is given z1, z2, all the way to zl. So one important thing here is that independence and conditional independence, they may be different. So you could have two variables which are not independent, and then once you're given a third variable, they might become independent. So that's actually pretty common. So maybe, yeah, so maybe one example could be if x is the house alarm ringing and y is maybe the neighbor calling you to tell you something is wrong in the house. And then z could be there's a burglar in the house, right? So it's getting a bit complicated. We can write this example down, right? So for example, x house alarm rings, y could be neighbor calls, because neighbor calls, and then z could be burglar. It's hard to write sometimes. Erase. In-house. So if we knew nothing about z, let's say that we didn't know anything about z, then I would say that house alarm rings and neighbor calls, they would not be independent, because the neighbor might be calling because the house alarm is ringing. However, if we're given that the burglar is in the house, then x and y become independent, you could argue, because the burglar could trigger the house alarm, and the house alarm has a probability of ringing whenever there's a burglar detected. And then the neighbor, if the neighbor knows that the burglar is in the house, maybe that's the reason why the neighbor calls, right? Anyway, there are many examples like this. So don't assume that if two variables are not independent, they're also not conditional independent, and also vice versa as well. Okay, next we have Bayes' rule, which is one of the most important rules in probability. So this is very useful when you want to relate P of x given y to the reverse, which is P of y given x, relating that to P of x given y. So we start with the conditional probability P of y given x, which is by definition equal to P of x y over P of x. Now we expand out. We use the chain rule on P of xy, and then we get P of y times P of x given y. So that's kind of how we're able to swap the conditional probability. So one way I like to use to remember the Bayes rule is to write down the chain rule in two ways. So for example, we could write down P of xy is equal to P of y, P of x given y. But we can also write this as P of x P of y given x. So now if you write it both ways, you can kind of decide to kind of divide by P of x and then putting that in the denominator, or you can decide to put P of y in the denominator of the other side. Okay, so that's kind of how I like to remember the base rule. A lot of times with base rule, we often expand the denominator, P of x. That's a marginal distribution. So in a continuous case, we basically integrate over all values of y. Sometimes we even use the chain rule to expand P of xy at the bottom. Basically now the bottom looks like the top, except that you have the integral. For the discrete case, it would be a summation, of course. For the conditional case, again, everything works. You just have to condition on the same thing in every term. Okay, so now let's take a 10-minute break and we'll be back with more probability. Okay, so let's continue. We're going to now review expected value. So in the two random variable case, the expected value of a function of random variables f of xy is just given by the summation over all possibilities of x and y of f of xy, p of xy. So this is the case when x and y are discrete. In the case where they're continuous, it's the same thing, but you just integrate all possible values of x and y. Okay, so yeah, for the multivariable case, more than two variables, we simply sum over all possibilities of all variables, and then same with the integral for the continuous case. So this is all the scalar case. So f, the function f, in the top two cases is outputting a scalar variable. But in general, f could actually be vector valued, meaning that there could be many components in the output of f. In this case, we just take the expectation component-wise. So basically, the first component of the expectation would just be expectation of the first component, and so on. Another way of thinking about expected value is the average value from the function of random variables. A lot of times, the expectation is actually taken on simply x or y. In that case, the function is just the identity function. So a lot of times, we may not even need to use these definition of expected value. Well, sometimes we do, but a lot of times we can actually use the properties of expectation to compute a pretty complicated expectation given the expectation of a simpler variable. So for example, expectation is a linear operator. So linear means that you can scale by a constant or you can add, and then the expectation would also be added as well or multiplied by a constant. Okay, so basically the expectation of a linear combination of variables is actually the linear combination of the expectations. So that would be the more general thing to write here. Okay, so that would be, let me just write that down. So in general, we actually have expectation of a summation, which is a linear combination of random variables, is equal to the linear combination of the expectations. Okay, so that's the most general version. So that these two properties here imply the one that I just wrote down. We have to be a bit careful. When we have two random variables multiplied together, the expectation of the product is actually not the same as the product of the expectation. So this is not true. If x and y are independent, then this is actually true. Okay, so moments. So expectation or mean or average is actually the first moment of a random variable. So other moments include covariance and variance. So I suggest you guys look on Wikipedia, for example, to get a more general sense of what moments are. But for us, we're just going to be focusing on covariance and variance. So first, let's look at covariance. This is the definition. Covariance of xy, written like this, equals to expectation of x minus e of x times y minus e of y. If you expand this out and simplify, you will get the result is the same as expected value of xy minus expected value of x, expected value of y. And as you can see from these expressions, the covariance is symmetric, meaning that you can actually exchange the variables x and y, and then it doesn't really change the covariance. So let's take a look at what the covariance means, at least mathematically. We'll probably come back to it a bit later. So whenever you see expectation, you need to ask yourself what exactly is the random variable inside. For example, on the very inside, we have expected value of x. So obviously x is the random variable inside, and then we're taking the expected value of it. Same for this part, expected value of y. So probably I'll just say e of y. Okay, so these two are actually constants because once you have taken the expected value, this e of x and e of y, they just become a number. So this part is not random. The parts that are random are the x and the y here. So because we have some randomness in the x and the y, we're now going to take the expectation of the entire thing. So what exactly does that mean? So basically we're multiplying the deviation of the random variable x from the mean. So x minus e of x is the deviation from mean. Okay, how about we write this down? So this is deviation from mean for x. And then this, of course, is deviation from mean for y. Okay, so basically, on average, x will be this value, expected value of x. However, because x is a random variable, sometimes it may be above the mean, sometimes it's below the mean. Whenever x is above the mean, the first term will be positive, and whenever x is below the mean, the first bracket here, this part, is going to be negative. So same for x and y. Same for y as well. So what this expectation is doing is basically we're going to randomly sample an x and y at the same time. And then we're going to multiply these two quantities together and see what we get, right? So, and then we're going to draw many samples. The way you can think of expectation is you can try many times and then take the average value, right? So now you can imagine drawing many samples of x, y. Sometimes when x is above the mean, y may also be above the mean. And then sometimes when x is below the mean, y can happen to be below the mean as well, right? And we can have the other cases as well. Sometimes when x is above the mean, y is actually below its mean, and vice versa. Sometimes when x is below its mean, y might be above its mean. So basically, the sign of the covariance tells us whether x and y tend to be above their means together, and also below their means together. So if it's a case that whenever x is above the mean, y also tends to be above the mean. And whenever x is below the mean and y is also below the mean, that means the covariance is actually going to be positive, because you will tend to have positive times positive in that case. But for other random variables, for other pairs of random variables, sometimes whenever x is above the mean, y might be below the mean. And sometimes that can be a consistent pattern between the two variables. We'll see some examples later. And vice versa, sometimes whenever x is below the mean, y just happens to be above the mean. If that behavior consistently happens, then the covariance is actually negative. So basically, whether covariance is positive or negative tells us how x and y vary together. Do they go above their means at the same together, or is one above the mean whenever the other one is below the mean? Right, so that's kind of what covariance tells us. Okay, so next, a special case of covariance is the variance. So the variance is actually just the covariance of x and x itself. Using the same formula, basically the y just becomes x. So we have e of x minus e of x squared. You can also simplify this to e of x squared minus e of x, all of that squared. Okay, and so the interpretation here is a bit simpler. We're simply going to sample many different values of x. check to see how far it is from e of x and then square that. So here you can see that the sign doesn't matter because we're always squaring the result. So this is just a measure of how spread out x is around the mean. The standard deviation is actually something that we use very often. It's actually just the square root of the variance. And there's also another commonly used concept, Pearson's correlation coefficient, usually denoted rho, the Greek letter rho of xy. It equals to covariance of xy divided by root variance x and root variance y. The denominator here is basically to scale the covariance to be between -1 and 1. So a covariance is -1 whenever x is doing exactly the opposite thing as y. So x equals -y. And then the covariance would be 1, the correlation would be 1 whenever x and y are always equal. Okay, so this is something that we should be careful of. So if x and y are independent, then the covariance of xy equals, well, this is the definition, e of xy minus e of x, e of y. And we know that for independent variables, we can actually split this e of xy into e of x times e of y. And then these two terms would then cancel out and you get 0. So independence implies covariance is 0. However, covariance is 0 does not imply x and y are independent. Okay, so let's continue. So we just covered expectation, variance, covariance. Now we're going to look at some conditional versions of them. Again, it's going to be the same as before. The only difference is that instead of e of f of xy, as we had before, we're now just going to add the conditional a variable for every term. So basically, if I just go back to expected value, well, that slide, the slide that I'm showing you next will be exactly the same, except that you have given z everywhere. Okay, so for example, the conditional expectation of f of xy given z is the same as summing over all the possibilities of xy or integrating them, and then multiplied by f of xy, the function here. Very often the function could just be x or y, and then multiplied by the conditional distribution p of xy given z. We also, of course, have the general case where we might be given many different variables. Okay, in that case, exactly the same. We sum or integrate over all the variables inside the function f, and then we multiply this function f inside the sum or integral with the conditional distribution of p of x1 to xn given z1 to zl. So these are the conditioned variables. And of course, as you can expect, we can also have conditional moments. So that means conditional variance as well. Everything's the same except that we're just going to be given some other variable z equals little z. And the definition basically stays the same. Basically, we make use of the definition of conditional mean in the definition of conditional variance. So for a normal variance, we didn't have this given z equals little z here. It used to be just e of x. So then the given z equals little z happens here, and then also happens again on the outside expectation. Of course, we also have the multivariable case, when we might be conditioned on many variables at once. In this case, it's exactly the same, right? Just replace the big Z equals little z with the list of z's, z1, z2 equaling the little z1, z2, and so on. Exactly the same. So the only thing to be careful of here is that with conditional variance, we need because we have two expectations for variance, each of those expectations must be a conditional expectation. So if I just go back to the original definition of variance, we have this expectation and that expectation. If it's the conditional expectation, then if it's the conditional variance, then both of the expectations need to become a conditional expectation. So let me just switch to the other slide so you can take a quick look again. Okay, again, we're going through this really, really fast because I expect most of you to have seen most of the stuff. There might be one or two things that are new, and you can always catch up on those. You can also come to office hours or ask on courses forum. But for the most part, we're not going to spend too much time on this material in class. So then moving right along, we're going to talk about entropy. So roughly speaking, I guess, or maybe I should say intuitively, the entropy measures the amount of uncertainty in a discrete distribution. So for now, we only consider discrete distributions. So for discrete random variable x, the entropy of x is defined to be expected value of the negative log of p of x. So we usually denote that as h of x. So how do we understand this? Well, if you go back to expectation, when we have expectation of some function, we simply sum over all possibilities of the same function multiplied by the distribution, right? So entropy is basically picking this function to be negative log p of x. So if I just go back to the other slide, hopefully you can now visualize, okay, so now f of x is the same as negative log p of x. So that's why we're going to sum over all possibilities of x. And then we take the function, which is negative log p of x, times our probability distribution, p of x. So here, because p of x could be 0, we actually define 0 log 0 to be 0. Usually the base b of the logarithm is e or 2. If the base is e, then the units of entropy is nats, and if the base is 2, then the units is bits. Usually in machine learning, we assume that the base is e for logarithms. In some other disciplines, like in high school math, you know that the log is always base 10 to begin with, at least. And then in courses like CS theory or maybe information theory, the base of the log is by default 2. So the entropy is actually another intuitive meaning of entropy is the amount of information inside the random variable. So the amount of uncertainty is actually related to the amount of information. Okay, so let's actually, maybe we can explain it a little bit here. So some properties of entropy. So for any discrete random variable, the entropy is always non-negative. And the entropy is 0 only if x is deterministic. And the entropy is maximized whenever the probability of x is always the same for all x. So that means when the distribution is uniform. So if we take the simplest case, then the coin toss, we can consider x to be the result of a coin toss. So let's say x is 1 if we get heads, x is 0 if we get tails. So if the probability of getting heads is always 1, let's say, that means that we always get heads no matter every time, right? So in that case, the entropy is 0. So that kind of makes sense based on our intuitive understanding, right? So if a coin is always heads, then there's no uncertainty in the coin flip. So then the entropy is 0. From an information theory perspective, you can kind of think like this. So if I flip a coin that is always heads, well, normally flipping a coin, I don't really know what it is unless I look at the coin or somebody tells me what the flip was, right? But if a coin is always heads, then telling me that you landed on heads isn't giving me any information. So revealing the outcome does not give me any information. There's no information gained from knowing the outcome. The other extreme is when entropy is maximized. So this is when we have a discrete uniform distribution. In the case of the coin toss, a coin that maximizes entropy would be a fair coin. So 1/2 chance of flipping heads or tail. So in this case, definitely there's a lot more uncertainty, actually the maximum amount of uncertainty. You can kind of compare to if a coin flips 98% heads and 1% and 10% tail. Actually, there's less uncertainty in that case, right? Because most likely it's going to be heads. But when it's half and half, that's when the amount of uncertainty is maximized. So that's when the entropy is maximized. Similarly, if we take the information interpretation, if a coin has 1/2 chance of heads and tails, and well, when I flip the coin, I have no idea what it might be. And if you tell me, or if I look at the coin to discover the outcome, then that kind of gives me the most information, right? It reduces uncertainty by the most amount. Whereas if the coin was 90% for heads, in that case, if you tell me it's heads, well, I already thought that most likely it would be heads. So I'm actually gaining less information that way. Okay. So this is a two-dimensional case where we could have the entropy of two variables. So again, it's the most entropy is maximized when both of the variables, so both coins, I guess, in this case, have 0.5 chance of getting heads or tails. And then the entropy goes to 0 whenever the coin flip is for certain. So this is kind of already a preview of what we're going to talk about now, the joint entropy. So the joint entropy is the entropy of multiple random variables. In the two random variable case, it actually looks very similar. The only difference is that the function inside the expectation is negative log of p of xy. So now it's the joint distribution instead of just the distribution of one variable here. So now after you know this definition, then the kind of writing it out just involves applying the definition of expectation. We sum over all possibilities of all the variables, and then we take the function, so negative log of p of xy multiplied by the joint probability distribution p of xy. In general, when you have more variables, it looks basically the same. Again, 0 log 0 should be treated as equaling to 0. So now the conditional version. So the conditional entropy h of x given y equals little y is actually equal to, so expectation, so the conditional expectation of negative log p of x given y. So here the given part appears in two places. One is the expectation is now a conditional expectation given y equals little y. And the other thing is that the function that we're taking the expectation of involves p of x given y. So this is now a conditional probability distribution. So now applying the definition of conditional probability distribution as well as conditional expectation, we take the function negative log b of p of x given y, so negative log b of p of x given y, and we multiply that by the distribution, in this case the conditional distribution of p of x given y. So this is a conditional entropy. How much uncertainty do we have when we're given one of the variables? Okay, so this is for when we know what the value of y is. So when we're given a particular value of y, this is what the conditional entropy is. more generally, we may not be given a particular value of y. In that case, the conditional entropy is actually defined as h of x given y. So we don't write y equals anything. Since we don't write y equals any particular value, we're instead going to take the expectation over y. Okay, so now we kind of have a nested expectation. So the way you read this is, first forget about e of y for now, right? Focus on this part. If we are given some value of y, little y, like the above, then we can always compute the resulting value using this formula here. If I'm given a different y, then this expectation will evaluate to a different number. So now I can always take the expectation over the value y that I'm now no longer given when I look on the outside. We can actually simplify this expression a little bit by first using the law of total expectation to turn the e of x, the nested e of x, e of y into the expectation over the joint expectation over x and y. Okay, sorry, I think I actually forgot to cover that. Let me go back a little bit. Okay, so that was actually all the way back here when we talked about conditional moments. The last part is actually the law of total expectation. So basically, when you have a nested expectation, where the inside of the expectation is a conditional expectation over some variables which are in the outside expectation, then we can actually merge all of the expectations together. So this is expectation of all the variables together of simply the function, and now the expectation is just a regular expectation, not a conditional expectation. Okay, so the pattern here is that we have nested expectation, where the inside expectation is actually a conditional expectation given the same variables as the outside expectation, right? So if you go back to the entropy slide, in this case, we have a nested expectation where the inside expectation is given y, which is the same as the outside expectation. So now we can merge them into a joint expectation and then writing out the definition of expectation. So this is the function log b of p of x given y and then multiplied by p of xy. Okay, and then if we want, we can kind of simplify this a little bit more. So the last step, actually is basically because p of x given y is equal to p of xy divided by p of y. So that's why the log of p of x given y is just equal to the log of p of xy divided by p of y, right? And then with logs, we know that whenever you're dividing, you can subtract them. Okay, so I will just write out the last step here. Okay, so that's the details from the second last step to the last step. So that's why we have p of xy multiplied by the first term here, and then minus p of xy multiplied by the second term here. Okay, and then a lot of notation here, but in general, for conditional entropy, we may want the entropy of x given a bunch of different variables y. So following the same argument, so basically this slide is just following exactly the same steps as the previous slide, except wherever the previous slide says given y, big Y equals little y, and then we have the expectation of just a little y here. We now have a bunch of different variables, right? So just to recap a little bit, the conditional expectation involves involves writing down the condition variables for the probability distribution here. So this is now a conditional distribution. And then the expectation is now a conditional expectation. So this is when we are given the individual values of y. In general, if we're not given the individual values of y, we would just take the expectation over all of the values of y. Just like before. And now, again, we're going to get a nested expectation with the inside being conditioned on big Y1 to YL. So these variables are basically exactly the expectation that of the variables that we're taking over on the outside. So that becomes a joint expectation. And then all the math follows the same as the previous slide. Okay, so not really gonna dwell too much on this. You can definitely take a look at these slides and work out the math a bit more slowly. Okay, so let's just move right along again. Talk about relative entropy or KL divergence. So KL divergence stands for Kullback-Leibler divergence. Leibler, I think is, maybe you guys can correct me on this. I think it's Kullback-Leibler. Okay, or is it Leibler? Okay, so let me know. Okay, so I usually call it a KL divergence. I almost never say the full thing out loud. Okay, so the definition of entropy is actually, again, summation negative sum of p of x log p of x. So now with KL divergence, we consider two different distributions, p and q. And here we assume that the support of p is a subset of the support of q. So remember, support of a distribution means the non-zero the set of x's such that p of x is non-zero or q of x is non-zero. Okay, so the KL divergence is actually written as d sub KL of p and then double pipe q. So this is equal to, defined to be negative summation of p of x log q of x. So the KL divergence has the interpretation of the distance or the similarity between two different distributions. Okay, just to be exhaustive, right? So a lot of the probability slides are basically information that you guys will likely find useful in machine learning at some point. Even if they may not be used very, very often. So some of these concepts, so for example, I use KL divergence quite a bit in robotics actually. KL divergence is also used in generative models whenever you see these AI algorithms that can actually generate realistic looking images, for example. So many of the generative models which generate images, for example, make use of the concept of KL divergence. Okay, so basically I want you guys to become familiar with all these concepts. And then in the future, whenever you come across something, you will kind of hopefully know that, oh, it's from the machine learning lectures. And then if you don't remember all the details, you can always go back and look. Okay, so the mutual information I of x, y is equal to h of x minus h of x given y. Also equal to h of y minus h of y given x. So the interpretation here is kind of the information gain if we're given one of the variables. So this is the entropy of x. This is the entropy of x when we're given y. So how much more information do we gain for x when we are given the variable y? Okay, and then using the definition, we can kind of write this out. So again, I think it might be useful to slowly work this out step by step, just plug in the definitions, and hopefully you're able to recover this expression. It's more of a practice in kind of the properties of log mostly. Okay, that was a lot of terms about probability. So we're now going to kind of talk about everything using vector form. So whenever we have multiple random variables, as you have seen in many of these slides, right? So here we have x and y, and then on the previous slide we had a bunch of stuff, x, y1 to yl, right? Sometimes we had z1 to zl for some of the conditional concepts that we covered. So all of that is a little bit annoying to write. So we're actually, in this class and actually in many machine learning papers and in future courses, you will see that all of these different random variables are going to be collected together into a random vector. So this is the vector x. So now if you perform any operation such as taking the expectation of this of this vector, then you basically just take the expectation of each component of the vector, and then this would be called the mean vector. Actually, in machine learning, basically everything is a vector, so typically we'll just say it's the mean. In machine learning, we basically assume everything's a vector. So now the concepts of covariance and variance. So obviously variance is basically how spread out each variable is from its own mean, and then the covariance is kind of a pairwise concept, right? So we can arrange them into a matrix. And this matrix is actually given by x vector minus e of x times x minus e of x transpose. Okay, and then you can do some simplifications and you also get e of x, x transpose minus e of x transpose. Okay, so we're going to talk a little bit more about covariance and variance matrices when we talk about Gaussian random variables later. Actually, again, this is called a covariance matrix, but in machine learning, because everything is basically a vector, we just say covariance. Okay. So now multivariate normal distribution. So this generalizes the normal distribution to multiple random variables. In machine learning, we actually simply just say Gaussian distribution. Well, I guess a lot of people say normal distribution, but in machine learning, people tend to say Gaussian distribution. And then in machine learning, because everything has multiple variables anyway, we kind of omit the multivariate, right? It's just Gaussian distribution. It is always implied that there might be many variables. This is a plot of the probability density function of the normal distribution. You kind of see that it's a bell shape, but then it's kind of, this is two-dimensional, of course, so it's a bell shape in 2 dimensions, in both directions. The integral, or the volume underneath the curve, will add up to 1. So how do we write this function down mathematically? In the single variable case, whenever x is distributed normally with mean mu and variance sigma squared, this was the PDF. So 1 over square root of 2 pi sigma squared times exponential of minus x minus mu squared over 2 sigma squared. In the multivariate case, the variable is now a vector, so a random vector. And so we say the vector x with components x1 to xn is distributed normally with a mean vector, or just a mean, and also a covariance matrix, which is just covariance. Turns out that this covariance matrix is always positive definite. So now we can kind of see the generalization of this formula to the vector case. In front, we have 1 over, so I mean the front is honestly not too important because this is just a constant and the shape of the function is determined by the exponential part. The constant is there to make sure that the integral underneath the function is equal to 1. Okay, anyway, in the multivariate case, we have 1 over root 2 pi to the power of n and then determinant of the covariance matrix sigma times exponential negative 1/2. Okay, so now this part is basically the generalization of a quadratic term in the scalar case. So in the scalar case, we have something squared, so that's a quadratic term. In the vector case, we have a quadratic form, with x minus mu vectors transpose, and then the matrix sigma inverse, and then x minus mu. So now we're going to actually figure out kind of how the quadratic form behaves, and this will actually tell us what the normal multivariate normal distribution looks like. So we're now going to hopefully recall some facts about the singular value decomposition. So the right singular vector of a matrix A with the largest singular value is actually the direction along the direction in which a unit vector becomes the longest after being transformed by A. So we were kind of looking at this when we were looking at SVDs. So when we're looking at SVDs, we're kind of saying, okay, so I guess the matrix, in this case, the matrix 1, 2, 0, 1 will modify each of these colored vectors into a different vector. So which of these vectors will actually become the longest after being multiplied by A? In the drawing, that turns out to be this vector V here. And then after multiplying by A, it actually becomes quite long, pointing somewhere in this direction. So that's the right singular vector corresponding to the largest singular value. Okay, so basically, mathematically, we can write V1 equals the argmax of x such that the norm of 2 norm of x is equal to 1 of the 2 norm squared of ax, right? It's a mouthful, but so that's why sometimes the math is a lot more clear, right? I mean, the math is clear when you look at it, but then it's kind of hard to say, right? So that's why we just say right singular vector with largest singular value. And this is what it means. So now basically looking at this 2 norm squared, while the 2 norm squared, as we know, can be written as a quadratic form. So 2 norm is the same as the vector transpose times itself, and then we can then take the transpose inside. So then you have x transpose ax. Okay, so basically now that we understand what the right singular vector is, we can start to understand what exactly this quadratic form is doing. Okay. So actually, we need to do one more step. In the Gaussian density, the middle matrix is not in the form of A transpose A. It's actually just a single matrix sigma inverse, right? And I mean, I suppose you could try to determine which A will have the property that A transpose A equals sigma inverse, but I mean that's a pretty useful thing to do, but it's not so necessary here, because we can now relate the right singular vectors of A to the eigenvectors of A transpose A. So because the right singular vectors of A are the eigenvectors of A transpose A, the direction along which a vector grows the most is actually given by the eigenvector of A transpose A. So that means the eigenvector of sigma inverse. So basically the direction of the eigenvector of sigma inverse with the largest eigenvalue will be the direction that a vector will get stretched the most. Okay, so I think this is a kind of a hard to follow, but hopefully when we get to the final result, things will make a bit more sense. Okay, so now last thing we need is that because sigma is symmetric, we can actually do the eigendecomposition of sigma inverse, which is equal to u lambda inverse u transpose. The U contains all the eigenvectors of sigma inverse. So that means that the eigenvector of sigma inverse with the largest eigenvalue is actually the eigenvector of sigma with the smallest eigenvalue. So basically, when you take the inverse, all the eigenvalues get inverted, right? So the largest of one matrix becomes the smallest of the other one, the inverse. Okay, so now these few slides, I suggest that you guys go through them slowly and many times after the lecture. But now we can finally combine all of them into figuring out what the normal distribution looks like. So here we have a kind of a top-down view of a normal distribution, so the contours of the PDF. The black arrow denotes the eigenvectors of sigma. And again, these will actually be orthogonal to each other because we know that U is actually an orthogonal matrix, right? So all the vectors inside U are orthogonal. So with normal distributions, we always have two principal axes which tell us the direction of the elliptical contours. Okay, so basically, when we take a top-down view of the Gaussian distribution or normal distribution, it will always be an ellipse or a concentric ellipsis. So this is basically stretched out circles. And then the principal axes, meaning that the major and minor axes of the ellipse are always going to be in the direction of the eigenvectors of sigma. So now, if sigma has a very large eigenvalue in one of the directions, then in that direction the distribution is more spread out. And in the direction where sigma has a small eigenvalue, those directions are pretty narrow, right? And this basically has to do with constructing the quadratic form using sigma inverse. So the direction where sigma has high eigenvalue, those directions will actually be the direction where sigma inverse has the lowest eigenvalue, meaning that the function doesn't grow very quickly. So that's why in those directions, the distribution is more spread out. Okay, so I think we'll just end here. I think that went by quite fast, especially for the multivariate normal distribution part. I think this part is definitely worth looking at a bit more slowly. So next time we're actually gonna work out a concrete example just to make sure that you guys understand how to relate the sigma matrix. So this is the covariance of the distribution to the shape of the distribution. So we'll see you guys next time.